Hello. In this module, we are going to analyze a refrigeration system, just like we did the heat engine system, the heat engine in the last part. So let's begin by defining what is a refrigeration system. First of all, its purpose is to transfer heat from a cold place to hot place, opposite to what nature does. So let's take a cold place at temperature Tc that we want to maintain, and to maintain it at Tc, we have to remove some heat. Why? Because maybe heat will be leaking to the cold place, because nature will try to transfer heat to a cold place, or for whatever reason. Suppose this is the cooling load. To keep it at Tc, we have to remove, let's say, an amount of heat. Let's say 5 kilowatt of heat has to be removed from a cold place. Suppose someone comes up with a black box and tells you, oh, that's so easy. This black box, just put it on your system, on the wall of your system, and it will draw that heat and take it out, Q dot H, to a hot place, TH. The hot place typically is the atmosphere. That's where you throw your, garbage into. Well, so Q dot C is being pumped out of your cold system and pumped into the atmosphere. And this is known as a refrigeration system. The purpose is to keep the cold place cold by removing a given amount of heat. All right, let's do an analysis of the system, do a boundary, make a boundary of the system's universe. The energy equation can be simplified. For this particular system, steady state, 0 becomes Q dot is Q dot C minus Q dot H. Again, we are using the Wien-Hip sign convention. So if you notice, Q dot C, Q dot H, these are all positive quantities. The arrows are showing the direction. So heat in is positive. That's why we are putting Q dot C is plus and Q dot H is minus. And of course, there is no work transfer at all. So that's our equation. It simply says Q dot C equals Q dot H. A second law analysis of this system will give us the entropy generation in the system's universe, which must be positive to satisfy the second law. Friction cannot be negative. Okay, Q dot is what? Q dot is, we have to split into two terms, Q dot C over Tc minus Q dot H over Th. See if you follow that. This has to be done over the entire boundary, and because the temperature is changing, we're summing over different parts. There are only two parts where there is a heat transfer, so it's Q dot C over Tc is the entropy that goes in, this is the entropy that comes out, and there is no this is the entropy generation. So the equation for the expression for entropy generation becomes Q dot H over Th minus Q dot C over Tc, and we have already proved these terms are equal. So if I say Q dot C and Q dot H are equal, it becomes 1 over Th minus 1 over Tc. Now we know Th is higher than Tc. This is the cold place, right? This is the cold place and this is the hot or warm place. So obviously hot place temperature Th is higher than Tc. So therefore inverse of that, this becomes a smaller term than that. Therefore this term become negative, because Q dot C is a positive quantity. So S dot gen being negative means it violates the second law of thermodynamics. It cannot be negative. Therefore, you know that somebody claiming that this is my refrigeration system, just a black box, automatically you have to do nothing. This box is going to transfer heat from a cold place to a hot place. You will say baloney. Nature will always transfer heat from hot to cold place. If you do the other way around, you have to somehow generate entropy somewhere. Okay, let's look at an alternative, the refrigeration cycle that really works. So this black box is now modified. Again, everything else being the same. This is Tc, and we are drawing a heat at a rate q dot c and throwing it into the atmosphere, which is at temperature Th at a rate qh, and we are supplying some net work into the system. Again, this is our systems universe, and we're going to repeat the same analysis. What do we get? So if we repeat the analysis, the energy equation gives us the EDT. Again, Q dot is what? Q dot C minus Q dot H. And external work minus W dot external. Notice net work is going in. If we use win heap, what do we substitute for external work? Negative W dot net. See if that makes sense to you. This is our Q dot, and this is our W dot external, which is the algebraic quantities. So therefore, we get an expression for Q dot H equals Q dot C plus W dot net, which should be intuitive. What is Q dot H? How much heat is coming out? And Q dot C and W dot net are how much energy is going into the system. If you treat energy just like mass, because both are conserved, and look at the boundary. Energy is flowing this way and coming out that way. For steady state, no energy should be accumulated. The EDT equals 0. So therefore, this plus Q dot C plus W dot net should be equal to Q dot H. So it totally makes sense. But I urge you to understand the connection between the energy equation and what we derived as an intuitive energy balance. In that will prepare you to analyze any type of system in the future. Okay, so the network that we need, then it becomes Q dot H minus Q dot C. So how will we define an energetic efficiency? Just like the thermal efficiency of a heat engine, the desired energy output divided by required energy input. What is the desired thing here? Is Q dot C. That's the load on your system. You want to remove Q dot C, so many kilowatt from a cold place. And how do you pay for it? With the work. Both are positive number. So that ratio is the counterpart of thermal efficiency for a refrigeration system. It can become more than one. That's why it's called the COP of a refrigeration system, which stands for coefficient of performance. Basically, it's an efficiency that can be more than one, so we call it COP. The COP of a refrigeration system can be 200%. All right. So recall that Q dot H doesn't participate in the definition because it's kind of like the waste heat. We are throwing it away. If you use the same refrigeration system, this black box, for a different purpose, suppose you say, I'm putting it between an outside which is colder than my house, and I want to transfer heat from outside to inside. In that case, TH becomes the house temperature, the temperature inside your room, and TC becomes the temperature outside on a cold night. Then Q dot H will become our desired heat transfer, right? In that case, it's called a heat pump. So basically, you can analyze a heat pump if you know how to analyze a refrigeration system. Just only difference is what is desired now becomes Q dot H, and you don't care about Q dot C. But let's stick to the refrigeration system. So Q dot C is our desired heat transfer. Tc is the desired temperature of the cold place, and Th is typically the atmospheric temperature. And W dot net is our required input. So if I use the analysis of the energy equation in the definition of COP, then we get the COP of a refrigeration system as Q dot C, W dot net, we can substitute W dot net is Q dot H minus Q dot C. So this becomes an easier definition. for whether a refrigeration system is ideal or not, this will always hold. If you know how much heat is going extracted from the cold place, how much heat is thrown into the hot place, from there you can figure out W.net and therefore the COP. Now let's do a second law analysis to make sure that such a system can work. Using the same diagram, entropy equation, if you recall, for the system's universe will give us 0 equals Q dot C over Tc, entropy that goes in, Q dot H over Th, entropy that comes out, universe. Well, if you manipulate this equation, you can easily show by multiplying and dividing by different terms, and I'm just skipping this step, that Q dot H over Q dot C, we have done this for the Carnot heat engine, would be given by Th over Tc plus Th over Q dot C. Basically, we are multiplying both sides of the equation by this term. Multiply by Th over Q dot C and you will get this expression. You can show that. So therefore, going back to the definition of COP of a refrigeration system, which is, if you recall, Q dot C divided by Q dot H minus Q dot C, if I divide top and numerator and denominator by Q dot C, then we can get 1 at the top and Q dot over Q dot C here minus 1. Any ratio, we can divide top and bottom by anything, and the equality will hold. Now, this term, if we substitute what we just derived, we end up with 1 divided by this big expression, Th minus divided by Tc minus 1 plus Th over Q dot C S dot gen universe. So look at this expression. Right off the bat, we know that this is greater than equal 0 because friction cannot be negative. Th, Q dot C, these are all positive numbers. So if there is more friction in the refrigeration system, then COP will become smaller. COP is kind of like the efficiency of the system. So that kind of understandable. So note that what will be the ideal refrigeration COP? In the ideal case, there is no friction. This will go to 0. And the ideal cycle, which is also known as the reversible cycle, recall, if there is no signature of a natural process, which is S dot gen, then this natural process can be reversed. This is the entropy generation is the permanent signature of nature. So a reversible refrigeration system, which is also known as the Carnot refrigeration system, is given as 1 by, so we are substituting this to 0, Th over Tc minus 1. So if just to make sure we understand that, this term goes to 0, so let me write it down, plus this goes to 0, so that becomes equals 1 by Th minus divided by Tc minus 1, multiplying top and bottom, again this is a remarkable formula, a very simple formula where you can get to the bottom of the COP of a Carnot engine by just knowing what is the cold temperature that you want to keep your cold reservoir at, the cold place at. And what is your hot temperature? Hot temperature is typically atmospheric. So even though a real refrigeration system may not be as efficient as a Carnot system can be used as a guiding light for efficiency for the COP. Just like the Carnot efficiency, if you recall, for a heat engine is given by 1 by Tc over Th. Notice for a heat engine, the higher the hot temperature, the higher will be the thermal efficiency. As you can see, the cold temperature is the atmospheric in case of heat engine. On the other hand, in a Carnot refrigeration system, Th is the hot temperature, the atmospheric temperature. The cold temperature is your desired cold place temperature. So suppose you want to keep your room very cold, so outside temperature is, let's say, 300 Kelvin, divided by, in that case, if you keep inside temperature also 300 Kelvin, look, the efficiency become infinity. COP becomes infinity. That means you really don't need it doesn't cost you anything. If outside is at 300 Kelvin to keep you inside at 300 Kelvin, just open the window. But if you want to keep the inside cooler and use a refrigeration system, you can see that if you are happy with just a 10 Kelvin difference versus if you want a room 20 Kelvin lower, 20 Kelvin difference, your efficiency, COP, will be off by a factor of 2. So the cost quickly rises when the temperature difference increases. Just to relate all these terms to a practical system, let's go to an animation of a refrigerator, a household refrigerator, but we don't have to go through all the details here. Just to understand the overall thing, so here's the refrigeration box. Where is my, what do we call refrigerator in thermodynamics is really this particular cycle that's going on here. And let's try to understand what goes into this refrigeration cycle. A fluid is circulating constantly, keeping this system steady, and its purpose is to extract Q.C from this cold place, which is called the cooling load. In the case of a household refrigeration system, there can be heat leaking into the system, or you could be opening and staring into your food. That also increases the load. Doesn't matter. Some engineer will calculate the load for us. A refrigeration system is designed to handle a particular load. So suppose you have a 5 kilowatt refrigerator. I know sometimes you use the unit called ton of refrigeration. It's just a simple unit conversion. A ton of refrigeration is about 3.2 or something kilowatt. Look it up. So let's stick to kilowatt. So you have to remove, let's say, 5 kilowatt of heat. Then Q.C is 5 kilowatt. So if somebody says the cooling load of a refrigeration system is 5 kilowatt, immediately you understand Q.C is 5 kilowatt. Someone says the cool space has to be maintained at, say, 0 degrees Celsius. You know the Tc is 0 Celsius means 273 Kelvin. So what happens here, the heat is now taken out, and here the fluid goes through what is known as the evaporator. It essentially boils. It absorbs heat whilst boiling at a very cold temperature, at Tc. And it becomes vapor, and that vapor is compressed by this compressor, and this compressed vapor becomes hot, and high pressure vapor is hot enough that it can cool down even in the atmosphere. It's so hot that it's cooling down in the atmosphere, rejecting Q.H. And as it cools to a liquid, that liquid goes to a device called an expansion valve, which is the magic device that makes the fluid cold. We will learn more about refrigeration in a future chapter. For the time being, you just need to appreciate that a refrigeration system is a closed system, as shown by this blue line, a blue boundary here that I just drew, or the red boundary that is shown in this animation, and heat Q.C goes in, is extracted from the cold place and thrown out into outside atmosphere, and the W.net that is consumed by the compressor in keeping this refrigeration system humming. I would suggest to you to go solve some problems from chapter 2.